An aircraft is flying a heading with 12 degrees starboard drift and making good a track 5 nautical miles to the left of center line of the airway but parallel to it. Find the relative bearing of an NDB situated at the center line of the airway 30 nautical miles ahead. Take a pause, read the question as many number of times as you want. Very, very commonly asked question, pretty much popular, especially with the Atpl subjects. So the question is definitely with respect to NDB, right? It's pretty clear from the question. And let's look at the parameters given here. You are actually tracking either from or to an NDB, doesn't really matter. You track out or you come inbound on your planned track. That's what you intend to do. But because of winds, because of inaccuracies in flying and navigation aids and stuffs, you might actually drift off. That's what's called as track error, drift, and all those parameters which you have studied in dead reckoning. In this particular scenario here, the aircraft is flying a heading with 12 degrees of starboard drift and making good a track 5 nautical miles left of center line. Now, you're given a drift here, which is 12 degrees starboard. So these kind of questions can be more approachable and easier if you kind of draw a diagram. And even for the exam, I would highly recommend you to place a picture before you figure out the answer, because that can kind of solidify the fact that you are ending up with the right answer. Now, to draw any particular line on your piece of paper, on your chart, whatever reference you have, you need to be drawing the track. Right? Track is exactly the line which you draw on the earth and therefore on the chart or on a piece of paper. In this question, if you look into it, it's given your off-track distance, but what is your planned track or what track are you actually flying is not mentioned. What else do we have here is a 12 degrees starboard drift. So with drift, there is nothing much you can actually do to kind of start with. If you need track, along with drift, you need heading, or vice versa, right? So there is nothing else other than either choosing a track, whichever you think is appropriate. You can assume your own track, or if you want, you can either assume a heading. Let me kind of assume a heading here to begin with. Let's assume a heading of say for example 270 degrees, and since we are actually flying the aircraft in this particular scenario, I would probably take it as magnetic. Doesn't matter, you can still take it as true, that's still fine. Now, it doesn't really matter what heading you are going to take, and for that matter, you will realize that at the end of this particular problem, the answer that is asked for is the relative bearing, basically the RBI indication. And for that reason, as I've discussed even the previous question, your actual heading doesn't really matter. The relative angle or the position is what matters, right? So if I assume a heading of 270, and let me apply the drift here. So drift that is given here is 12 degrees. And pay attention to the fact that it is a starboard drift. Now, just to give you a small heads up here, a starboard drift, or more appropriately, a starboard drift correction is provided when an aircraft has a tendency to drift towards starboard. That's why it is called as a starboard drifting case, right? In that case, your track would be probably to starboard of your heading, right? So if I take an aircraft here, say for example, if I place the aircraft at a random heading of say for example 045 degrees, with 12 degrees of starboard drift, your track is going to be to the starboard of your heading, which means drift, as you all know, is always measured from the heading towards your track. Here, track being to the starboard of the aircraft, it is a starboard drift, and therefore 12 degrees of starboard drift, as mentioned in the question, is going to give you a track of 57 degrees, true or magnetic. Right, so basically drift or drift correction applies to the heading, and you can actually find out the track. So if it is 12 degrees starboard, you add it to your heading to get your track. So perfect. Here drift is 12 degrees starboard and you have the heading of 270. Therefore, the track which you would be getting is 270 plus 12 degrees because of the starboard drift, and that's going to be 290, correction, 282 degrees, and again magnetic because we have it from the magnetic heading. All right, perfect. Now one of the questions which we have discussed earlier, and I definitely dropped the link up here, we have specifically explained the fact that if the drift is kind of derived from an indication from an instrument like an ADF, which can definitely tell you what the drift is, right? So if the ADF reading is 190, it's 10 degrees starboard drift moving away from the station. You know all those things. If it is, say, if the ADF indication is 20 degrees, you have 20 degrees of a starboard drift, which is moving, in this case, towards the towards the NDB. So ADF can give you a drift indication. All those drifts are actual drifts. The drift actually experienced by the aircraft, and for that reason is why the pilot is able to read it from the instrument. But in this particular case, the drift is just mentioned straight in the question. It's not derived from any ADF indication. It's just given 12 degrees starboard drift, and hence for that reason you must consider it as a planned drift. So drift, for that matter, in this question is the planned drift. Now the point here is, since we are looking at a planned drift and we are deriving the track from the heading using this planned drift, the track which you obtain is also the planned track. The track which you intend to fly even before the flight, not the actual track or the track made good. That's what I'm trying to tell you, right? If the drift is given from an instrument reading, like an ADF or so, it's going to be the actual drift, and therefore the track would have been the track made good or actual track. In this case, the drift is just given without any indication from the instrument. It's just given straight in the question, and that is going to be the planned drift, and therefore you obtain the planned track. Now, when you have the planned track, you have some kind of a value to start with, because whatever, as I told you before, whatever you put on your paper as lines is going to be your track, not the heading. So we have a planned track of 282 degrees magnetic. Let's now put this into picture. The radio navigation aid which we are looking at is the NDB. So let's draw the NDB in place. Right, so this is the NDB. We're looking at a track of 282 degrees. So let's draw the track straight. So this is a track of 282 degrees magnetic, right? Now, we have the NDB in place, we have the track drawn in place. Now, if you look at the question here, it's given that even though this is your planned track, so this is basically your planned track, which is usually indicated using a line with two different arrows. Now, it's always a common concern or a point of confusion for students in general to identify whether the aircraft is moving towards the navigation aid, in this case it's NDB, or is it moving away from the NDB. And to kind of clarify that and clear the air, they have mentioned it in the question, but towards the real part of it, very clearly, that the NDB is situated at the center line of an airway 30 nautical miles ahead, which means the NDB is ahead of the aircraft, and for that reason the aircraft is approaching towards the NDB. On the contrary, and a question which we would be looking later, if the NDB was behind the aircraft on the same track, then the aircraft should be moving away from the NDB, right? So in this case, for the aircraft to be on a track of 282 degrees, and for the NDB to be ahead of the aircraft has to be somewhere towards this side rather than to this side, right? I hope that makes sense. And therefore, let's place the aircraft here. So we're looking at a side over here. So if I draw a line straight like this, we're looking at this particular side here. All right, now let's place the aircraft. Before we place the aircraft, we need to find out where the aircraft would be, and it is very likely that the aircraft would not be on a planned track because of drift factors or inaccuracies in navigation or the aircraft system and stuff. You might actually drift off, and now we have something called as a track made good, even though it is a bad track. Or the actual track, as we call it. To find the actual track, what they have given you this question is, they have told you that the aircraft is making good a track is more appropriately the track made good, or the actual track of the aircraft, and that is 5 nautical miles to the left of center line of the airway, but parallel to it. Couple of words put together here. Let's kind of disintegrate this and look piece by piece. Number one, the aircraft is found to make a track made good that is 5 nautical miles left of a center line. Now, what defines a center line is this particular track here. You're supposed to be on this track, right? So this particular track which we're looking at is the center line. This is the center line of the airway, right? That's what's called as an airway. Now, if you go back to regulation sessions, or if you have even gone through the RKBALI document, it will say that the airway can have a buffer of 5 nautical miles to either side. That is 10 nautical miles is kind of dictates the airway boundary, 5 nautical miles either side, right? And for that reason, if I take a 5 nautical mile section on both sides, of this particular center line, the aircraft could be anywhere within this 5 nautical miles on either side and still be within the airway limits as per the ICAO regulatory limitations. Alright, so in this question you can see the aircraft is actually found to be 5 nautical miles off to the left of center line. And since we know that the aircraft is tracking towards the NDB, I've kind of highlighted the blue area there. And now it is told that the aircraft is to the left of center line and off by 5 nautical miles. Alright, so the aircraft is 5 nautical miles to the left of center line, 30 nautical miles from the NDB. So NDB, we can have an association of a DME or a GPS system, and therefore it can provide you with a distance, and hence you have a 30 nautical mile distance right there, right? Now, which means that the aircraft is right here. Now, to place the aircraft here, that is where you need to have the heading. And in this particular question, we have actually assumed the heading to be 270 degrees magnetic. So let's draw an aircraft that is oriented at 270 degrees. That should be more or less like this. I'm drawing the aircraft is a bit bigger for us to kind of analyze the ADF indication. And to understand the ADF indication, as you discussed earlier, it's always appropriate to draw a circle around the aircraft, which is going to make the understanding a bit more easier and better. Now you can see that the aircraft has been flying so far parallel to the airway. So let me just put a parallel thing here. It has been flying parallel to the airway so far, and now it has to fly this particular track if it wants to head towards the station, towards the NDB, right? So this is the track that needs to be flown, right? So this is basically the track to be flown to the station. So I'm kind of disintegrating this question into small parts so you can understand it better. So we understood where the aircraft is it moving towards the NDB or away from the NDB? We saw whether it's to the left or right of the center line of the airway and how far is it off to the left or right. It's 5 nautical miles given there. We have placed the aircraft because we know the heading of the aircraft. We have drawn a dial around the aircraft because that is going to be more a pilot's perspective. Now we know that for the NDB, the ADF is the aircraft component, and that is going to show you exactly where the NDB is. It is absolutely not bothered about what your heading is. It's more to do with the relative bearing than the actual value of the heading. So let's place the ADF needle here. The ADF needle is actually going to point towards the track which you need to fly to reach the NDB, and that's the beauty of using an ADF. It will exactly tell you what track to fly to reach the NDB. You either have to find the track or kind of read the track straight from the indication, depending upon whether it's an RBI or RMI. So we assume that here we have an RBI indication, right? We'll also see what the RMI indication would be a bit later. Now, and that particular track which the ADF is showing would be a magnetic track to the station. So we're looking at a magnetic, point number 1, point number 2 it's a track, point number 3 it's to the point number 4 is not to the aircraft but to the station or the navigation aid, and that's what we call as the QDM, magnetic track to the station. That is nothing but the track to be flown to reach the station, right? That is a QDM, right? Perfect. You're asked to find out this particular RBI indication. Right now, to have the RBI and RMI in place, we'll just talk about that a bit later on how that is differentiated. But as of now, let's see what is the particular value that is indicated by the relative bearing indicator. Right. So the heading of the aircraft is 270 degrees. Let's draw a very quick RBI. So we have the aircraft. Always the center is how the pilot would be seeing it in the cockpit. And then we have a dial around it because an instrument dial that's straight here. Now, to understand an RBI, the first point to understand is RBI measures relative bearing, and that's a very common thing. We'll talk about that later. But the head of the RBI is what is more important here, and that's always the nose of the aircraft, which is taken as a reference and hence marked as 0. Right now, in this particular case, you can see that the aircraft kind of point towards somewhere in this direction to the right of the nose. You can see that in this particular diagram here. Let's kind of zoom out the diagram to see the entire picture here. So basically we are looking at this particular angle, and that is going to be the value indicated over here. And now we know that since being RBI, the head of the RBI is always 0. That's something which you have to remember. The relative bearing indicator takes nose as a reference or datum, and hence it is marked 0. Right? And now it measures relative bearing to the right of that particular nose, and that's going to be the indication of the ADF. Let's find that out. So basically I need to find out this particular angle which I've actually marked here in blue, right? And what I'm trying to do is, you can find out this in a couple of other ways, but one of the understandable ways or easiest ways would be to kind of divide this angle into 2 different parts. Here, as I'm trying to draw a line that's kind of parallel to the planned track. So what we have here is the planned track, and this is the track made good, or actual track which the aircraft flew so far, right? So I have drawn a yellow line here which is kind of parallel to the planned track, which means if I don't do anything about it, the aircraft is going to kind of fly through this yellow line, right? Now this yellow track is going to divide this particular angle into 2 different parts. Angle number 1 made by the nose of the aircraft with this track that is parallel to the planned track, and angle number 2 is between the planned track and the track that is to be flown to reach the NDBs. Look at these 2 angles very, very carefully and see if you can find out these 2 angles. Now, one of the easiest angles to find out is definitely angle number 1, because that is made between the heading and the planned track. We know both of them, right? The planned track is 282 degrees. We found that out here. We have already marked that, 282 magnetic. Therefore this track is 282 degrees magnetic. The heading of the aircraft is an assumed heading of 270 degrees, and therefore the angle between 270 and 282 is going to be 12 degrees, right? So that is actually in place straight there. Angle number 1 is already there. Angle number 2, though it's a bit different, it's kind of off navigation thing, but still it's quite easy. You can go back to your old school basics. We have 2 different parallel lines here. So basically we have drawn, this is the planned track, and this is your the track which I've actually drawn parallel to it, right? So you can see these 2 tracks, and for these 2 tracks, this particular track that is to be flown, this particular line is what becomes as a transversal. And since that is a transversal, you can see that these 2 angles would be same. 2 parallel lines cut by a transversal, these angles are going to be the same, all right? And therefore, let's find out the angle. So this angle being angle 2, you can find out that what this angle would be. So it's the angle between the planned track and the track that is to be flown, and in dead reckoning this angle is more appropriately called as a closing angle. Now you know how to find a closing angle. That is simply by applying the concept of 1 in 60 here. Remember, you have to apply 1 in 60 in such instances. It will be very, very easier. 1 in 60 is a concept that is mainly made to be used in the aircraft. But one thing to keep in mind is that it has to be applied only for smaller angles, and more appropriately angles less than 20. Even with 20, it's going to be quite erroneous, but definitely not about 20. So let's find out what this angle would be. To find this angle, we are looking at this particular triangle here. So let me kind of just highlight it very quickly for you, the triangle which is right here. And if you apply 1 in 60 to this triangle to find out the closing angle, see over here, it's pretty clear that 1 in 60 says, if you're off by 1 nautical mile over 60 nautical miles, your error is going to be 1 degree. Closing angle or track error, 1 degree. So we have 30 nautical miles distance here, off by 5 nautical miles. The closing angle is going to be 10 degrees. So you can find out that straight away as 10 degrees, or if you want to apply the equation, then you can use the equation as well. Let's try doing it using the equation as well. So 1 in 60 is basically distance off by distance gone into 60, and that is going to give you the track error. In our case, we have more appropriately the closing angle here, and therefore that is distance off divided by distance to go into 60. By definition, it might be a bit different, but practically it's going to be the same, right? So distance off is 5 nautical miles divided by distance to go is 30 nautical miles. So we are looking at this particular triangle here. So we have the distance off right here, and the distance to go is this particular leg over here. And remember, that is 30 nautical miles. The arc which you have drawn, you can recollect that. We have marked the 30 nautical mile arc straight here. Yeah, so distance to go is 30 nautical miles, distance off is 5 nautical miles. So 5 nautical miles divided by 30 nautical miles into 60, and that's going to be 10 degrees as your closing angle. Now once you get that angle as 10 degrees, that is same as angle number 2, which is 10 degrees here. So these two angles are same. So we have both the angles now. Angle number 1 is 12 degree, angle number 2 is 10 degrees. Therefore the total of these two would be 22 degrees. So this is the angle of the track to be flown, which is the angle toward the track towards the NDB from the nose of the aircraft, which is what is called as the relative bearing. So it's more appropriate, this is 22 degrees relative, right? And that is what the ADF is going to indicate is 22 degrees. If I put the same thing on this particular figure here, you will have 0 to 2 degrees indication here, which is what is the relative bearing. Now, if you have chosen a heading other than 270 degrees, you might be getting different values for your track made good, the track to be flown, or the planned track. That's it. The relative bearing, which means the angle made, the clockwise angle between the heading and the track to the station is still going to be 22 degrees. In this case, we know that our heading is 270 degrees, so let's put. So we have taken a heading of 270 degrees magnetic. We got a relative bearing of 22 degrees. Relative. Now what does this heading and relative bearing gives us? So if you add the heading to the relative bearing, you practically from the figure you can see will get the track which you need to fly to reach the NDB. So your heading is right here, and if I add this 22 degrees to your right, I'm going to get the track which I need to follow to the NDB. That is the QDM, or magnetic track to the station. That is QDM. And this is what your radio magnetic indicator, or RMI, is going to show. Let's see how the RMI indication would be. So having said that, I believe the RBI indication is quite clear to you. Let's see how the RMI indication would be, and let's compare these two for one last time. So always it's easier to understand this by drawing the aircraft being at the center, and then you have a dial around the aircraft, right? Now, unlike an RBI, in case of a radio magnetic indicator, what we do is we have the heading as the head of the dial. Therefore, the head of the dial is going to be a heading which is 270 degrees in this case. And now it doesn't matter whether it's RMI or RBI. This is one thing which you have to keep in mind. All these ADF instruments, they actually measure the relative bearing. Loop theory, loop antenna, I hope that portion is clear to you. It simply measures the relative bearing by trying to identify the phase at which the radio waves hit the vertical elements of the loop antenna, right? So it doesn't matter with RBI or RMI, it's going to measure the relative bearing. So even what RMI measures is also the 22 degrees of relative bearings, and therefore the needle is going to indicate exactly the same as that of RBI. You can see the orientation of needles in RBI and RMI which I have drawn is the same. They look like two parallel needles, and that's how it is. The needle is rotated by equal amount of 22 degrees. But what happens in case of an RBI is the same 22 degrees is rotated by taking the nose as 0, and in case of RMI the same 22 degrees is rotated taking the head as the heading of the aircraft, 270 degrees. Therefore, the kind of math which we do here by adding the heading to relative bearing is automatically done by the RMI dial. Therefore, when you add these two, you get 292 degrees, and therefore it's magnetic here, which is nothing but your QDM, and that's exactly what your RMI is going to show you. 292 degrees magnetic. So remember, do not confuse with what RBI and RMI measures. They both measure relative bearing, but what RBI indicates is relative bearing, what RMI indicates is the QDM, or magnetic track to the station. Alright, this is how an RMI would look like. You can compare RBI needle with the RMI dial with the RMI dial, and you see how they're different. They're different by only the fact that in case of an RBI, the head of the RBI is 0 or nose, but head of the RMI is the heading, right? So I believe you have a basic understanding of all these things. Otherwise, it's too early for you to look into this particular question. Basically, this is the answer to this question is you have to find the relative bearing of the NDB indicator in the ADF is 22 degrees. All right, that's it. Now, let's look at a very, very similar type of question here. I would recommend you to kind of stop the video and do